Welcome to our very first lecture on non-chordates. Today, we are going to explore the fascinating world of the phylum Porifera, commonly known as sponges. You might think of a sponge as just a synthetic yellow block next to your kitchen sink, but real, living sea sponges are incredible animals. They have survived for hundreds of millions of years and represent the very dawn of animal life on Earth. Let us dive in and discover how these simple creatures thrive without brains, hearts, or even true tissues. Now that we have introduced our topic, let us build an intuitive understanding of what a sponge actually is. Imagine a bustling city where there's no mayor, no central government, and no roads. Yet every single person knows exactly what to do to keep the city thriving. This is exactly how a sponge operates in the ocean. They are the ultimate living water filters of the sea. They sit quietly on the ocean floor while constantly pulling water through their bodies. Even though they lack a central nervous system or organs, their cells work together in perfect harmony to ensure the survival of the entire organism. Building on that intuitive picture, let us look at the formal biological definition. The word porifera literally translates to pore-bearing in Latin, which perfectly describes their appearance. They represent the most primitive group of multicellular animals, known scientifically as parazoa. Unlike humans or even insects, sponges exhibit what we call a cellular level of organization. This means their bodies are built from loose aggregations of different cell types that do not form true tissues or organs. Each cell is somewhat independent, yet they cooperate just enough to keep the sponge alive and functioning as a single biological entity. Since they lack true organs, you might wonder how they eat and breathe. The answer lies in their defining characteristic, the unique water canal system. This system is driven by specialized flagellated cells called choanocytes, or collar cells, which act like tiny motors. Their beating tails create a current that pulls water into the sponge's body through thousands of tiny microscopic pores called ostia. The water then circulates through internal canals or a central cavity called the spongicoil, where the cells capture food and oxygen. Finally, the filtered water exits through a large opening at the top called the osculum. To make this process completely clear, let us look at this cross-sectional diagram of a sponge. Notice the blue arrows representing the flow of water. You can see the water entering through the small pores on the sides, which are the ostia. Once inside, the water enters that large central empty space, the spongocoel. Look closely at the inner lining of this cavity. It is covered in choanocytes, or collar cells, which are actively pumping the water and capturing food. Finally, follow the massive blue arrow at the very top. This shows the wastewater shooting out of the osculum, far away from the sponge. Now that we understand their internal plumbing, let us discuss how they maintain their shape. A sponge's body is supported by a skeleton made of microscopic needle-like structures called spicules, which can be made of hard silica or calcium carbonate. Some sponges instead use a flexible protein called spongin. Biologists actually use the composition of this skeleton to classify Porifera into three main classes. First, we have Calcarea, which have calcareous spicules. Second, Hexactinellida, known as glass sponges, which feature beautiful six-rayed siliceous spicules. Finally, Demospongiae, the largest class, which possess flexible spongin fibers, siliceous spicules, or sometimes both. Beyond their fascinating biology, we must ask why sponges matter to the world at large. Sponges are the unsung heroes of marine ecosystems because they act as massive biological water purifiers. A single sponge can filter thousands of liters of water in a single day, removing bacteria and organic particles to keep the ocean crystal clear. Furthermore, their complex internal canals act like underwater apartment complexes, providing safe habitats for thousands of tiny marine species. In the medical field, sponges are incredibly important. To defend themselves, they produce unique chemical compounds that scientists are currently using to develop powerful new anti-cancer and antibacterial drugs. To truly appreciate how a sponge survives without a heart to pump blood, we have to look at the physics of its water canal system. The sponge relies on the principle of continuity from fluid dynamics. This principle gives us a simple mathematical equation. A in times V in equals A out times V out. Conceptually, this means the volume of water entering the sponge must exactly equal the volume leaving it. Let us break down the symbols. A in is the massive combined area of all the tiny internal feeding chambers, measured in square meters. V in is the slow velocity of water inside those chambers, in meters per second. On the right, A out is the area of the single exit hole, the osculum, and V out is the velocity of the exiting water. Because the internal area is huge, water moves very slowly, giving cells time to eat. As the area shrinks at the exit, the velocity must increase dramatically to shoot waste away. Before we move on, let us see this formula in action with a concrete example. A marine biologist finds that the total internal area of a sponge is 0.5 square meters, and the water moves at a slow 0.002 meters per second. The exit area is 0.01 square meters. We need to find the exit velocity. We start with our continuity equation. Next, we substitute our known biological values. Multiplying the left side gives us 0.001 cubic meters per second, which is the constant flow rate. To isolate the exit velocity, we divide this flow rate by the exit area of 0.01. Calculating this gives us a final answer of 0.1 meters per second. Physically, this means the water shoots out of the top of the sponge 50 times faster than it moves inside the feeding chambers, ensuring the sponge does not breathe its own exhaust. Now that we have calculated how fast the water moves, let us look at how much water is actually being processed over time. Sponges are incredible filters that work continuously, day and night. To measure their ecological impact, we use a simple volume formula. V total equals Q times T. Conceptually, this just scales up the per second filtration rate to cover any time period we want. V total is the total volume of water filtered by the animal, measured in cubic meters. Q is the volumetric flow rate, which tells us how much water moves per second. If you recall from our previous calculation, Q is just the area times the velocity. Finally, T represents the total time elapsed in seconds. If the flow rate increases, or if more time passes, the total volume filtered will increase proportionally. Let us apply this formula to see the true daily impact of a large barrel sponge. We are given a constant internal flow rate of 0.001 cubic meters per second. We want to find the total liters filtered in one full day, which contains exactly 86,400 seconds. We start with our volume equation and substitute our known values. Multiplying the flow rate by the seconds in a day gives us 86.4 cubic meters. Because cubic meters can be hard to visualize, we multiply by 1,000 to convert it to liters. Our final answer is 86,400 liters of water filtered per day. Physically, this means a single brainless animal sitting completely still filters enough water every single day to fill a large backyard swimming pool. We have covered a lot of ground today, so let us review our key takeaways. First, we learned that the phylum Porifera represents the simplest multicellular animals on Earth, surviving beautifully without true tissues or organs. Second, we saw how their specialized water canal system, driven by choanocytes, acts as their lifeline. Third, we applied the physical principles of fluid dynamics to prove how they slow water down for feeding and speed it up for waste removal. Finally, we highlighted their irreplaceable role as the ultimate biological filters of our oceans. You now have a solid, mathematical, and biological understanding of sponges. Excellent work today, and I will see you in the next lecture.